All right, everybody. We start with some review. So, quick recap. We talked on Wednesday. We talked about molecular and electron geometries. Everybody remember this graph or this chart? Ish. Remember that it existed, hopefully, even if you don't remember the specifics. Vaguely, it's fine. So, just a quick 30-second recap. The first column are all the electron geometries. Those are all the basic geometries where if you put a bunch of things that push against the other electron domains, they're always going to arrange into one of these 5 basic shapes. Right? There are a couple that go past that, but they get really uncommon once you get past it. You can have 7 electron groups, and that one is called a pentagonal bipyramid. You can maybe extend this idea of a trigonal bipyramid shape. Looks like 2 3-sided pyramids stacked on top of each other. You could think of octahedral as being 2 4-sided pyramids stacked on top of each other. Pentagonal bipyramid would be a pentagon around the middle with a 5-sided pyramid stacked on top of a 5-sided pyramid, which would look really weird, right? Basically, you start running out of space. You don't really have anything much past this octahedral shape because you start running out of space to put the electrons. So this is about as far as the common cases go. And a reminder with these is that the electron geometries are always going to be this first column, but if you have lone pairs, then what you can actually observe looks a little different. And that's what we call the molecular geometry. And I realize you can't see the names for this bottom row. So give me a second. All right, so the bottom row is called octahedral, square pyramids, square planar, T-shape, or linear. So this is sort of a capstone skill. This is going to be one of the sections of your midterm is going to be draw the Lewis dot structure. What's the electron geometry of this compound? What's the molecular geometry of this compound? Molecular geometry always comes from the electron geometry. You start by assigning the electron geometry, which is always one of this first column. And then if there are lone pairs, there's often a different name for the molecular geometry that's based on the electron geometry. So, and the way that I show this or do this on the test is basically show me the Lewis dot structure, show me the electron geometry, write the electron geometry, write the molecular geometry for these compounds. Nomenclature is a separate section on the midterm though, so I'll actually give you the formulas in this case, so you don't have to remember your prefixes. So let's give this a few minutes. Try this: phosphorus trifluoride, sulfur dioxide, and methanol. Can't remember the names of the geometries, at least try to draw them using those wedges and dashes. Did that a little louder? Wedges are, yeah, wedges are pointing towards you. and then the dashes are behind the fluorine. So remember, start with your Lewis dot structure. Go through that procedure. Put the middle atom in. Assign electrons around it. All right, so start by counting up your valence electrons. And place your center atom and the atoms around it. How do I know phosphorus goes in the middle? It's less electronegative. It has more vacancies. All right, and then we start by bonding our 3 fluorines to the phosphorus. We're bonding 3 fluorines to the phosphorus. We just used 6 electrons. Remember, every bond is 2 electrons, 1 from each atom, right? So we have 20 electrons left. Fluorine's more electronegative, which means we should fill its valences up first, because it gets first dibs on the electrons. So how many electrons are we going to use if we fill all the fluorine's valences? 6 for each fluorine, so a total of 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 2 electrons left. Fluorine's super electronegative, so should I give the extra pair of electrons to one of the fluorines? Why not? They already have full valences. Can they break the octet rule? No, fluorine's in the second row. It's a hard no on going past 8 electrons. So, luckily we have a place to put those electrons. We've got a phosphorus that still needs 2 electrons to get to having a full valence. So we finished criteria 1. Use the right number of electrons, right? We filled criteria number 2. Everything's got a full valence. About criteria number 3, do we need to worry about formal charge in this case? It doesn't seem like there's another way we could rearrange them, but for practice, we could look at this. How many electrons does each fluorine have? It has a total of 8, but 7 that it owns, right? Because the bonded ones that don't count as full ownership. And how many does it have on the periodic table? Also 7. So that means all of our fluorines have a formal charge of 0. Phosphorus owns 2 outright, plus another 3, so a total of 5. And it's got 5 valence electrons on the periodic table. So fluorine's also stable. Sorry, phosphorus is also stable. So we're good. We did our Lewis dot structure right. What's the geometry going to look like? What's the electron geometry going to look like for the phosphorus? It's got 3 fluorines around it. And does the lone pair still take up space? Yeah, it pushes away everything else, even though we can't see it, right? So we have 4 electron domains, 4 areas or volumes that are taken up by electrons. So they're going to space themselves out. When we have 4 electron domains, what is that shape? So the electron geometry, I'll switch back to that other figure here for a second. So I really like this figure with the exception of it says number of electron pairs, but I don't like that. So switch the word electron pairs with electron domains. So we got 4 things taking up space around a central atom. Our electron geometry is tetrahedral. And our molecular geometry, if there were no lone pairs, our molecular geometry and our electron geometry are always the same. If there's no lone pairs, then you can see everything. You could see all of the different atoms. So our electron geometry matches our molecular geometry. However, in this case, we do have some lone pairs. And so if we were trying to draw this in 3 dimensions, we'd have the phosphorus at the middle. We'd have a fluorine down to the left, pair of electrons in the board, in the plane of the board, pointed upward. A fluorine behind the board and a fluorine in front of the board. And you can kind of see how that gets these, they're further apart than 90 degrees, right? This is why it rearranges like this in 3 dimensions, because if we forced everything to be 90 degrees, that would actually force these electrons to be closer than they need to be. We have extra space because we have 3 dimensions to work with. And the conventional way to do it, there's actually several ways you can draw a tetrahedral shape with these wedges and dashes. The most common way to do it is to put 2 of your electron domains in the plane of the board, so flat. And then you put 1 forward and 1 back, kind of pointed generally in the same direction. So it looks almost like they're equally spaced out, like it's close to 120 degrees. Okay, exactly. If it was only 3 electron groups, if we didn't have the lone pair here, then yeah, it would flatten out and become trigonal planar, because then we can get a whole 120 degrees. Right? And so the further apart we can get these, the better. The furthest apart we can get 4 pairs of, or 4 groups of electrons is this tetrahedral shape. Right? And so that's what this first column means. Number of electron domains is how many things are taking up space. Because the number of things taking up space dictates how far apart they can be. So in this case, once we know the electron geometry, we do have a lone pair that we can't really see. But that just because we can't see it doesn't mean it's not still there pushing on the other electrons. So if we just erased that, now we only have 3 atoms attached to the phosphorus, but we still have the 4th thing taking up space that we can't see, the invisible electrons. So the molecular geometry is, what does it look like when we can't see the electrons? And they don't flatten back out. Just because we can't see the electrons doesn't mean they're not there, right? This is something that people struggle with. It's not like all of a sudden by erasing the electrons, it switches to being trigonal planar. The electrons are still there. We just can't see them. So we actually get this other shape, which we call a trigonal pyramid, which basically still looks kind of like a tetrahedral shape, just flattened out a little bit. So still looks like a three-sided pyramid. It's just a really, really shallow three-sided pyramid. All right, so full credit on the test. The way that's written, let me pull up the practice test so we can see this. And I'll show you what the formatting looks like. You get a sneak peek at your assignment for a week from now. All right. I guess while we're doing this, this is as good a time as any to talk about the midterm, which will be 2 weeks from today. We have one more week of March left next week. And then the first week of April is midterms. So we'll take the tests on either Thursday or Friday, probably Friday. I'll give you the whole week to prepare for it. Especially since I don't think I'm officially on duty that week, because I think that's our spring break at college. Our spring breaks are offset by 1 week. So we'll probably take it that Friday, but your assignment starting next Friday, your assignment, actually I'll probably give it to you on Thursday of next week, is basically practice test. You get a whole week to study, and the practice test looks identical to the real test. Formatting is identical. All that's going to change is on the definition section on the practice test. If it says electron, maybe I'll write orbital instead. Right, but it's still going to be 10 points of vocabulary. It's going to be 10 points of basic math where you just do your sig fig rounding. I'm going to test you on your sig figs, in just mostly just in one part. Test you on your nomenclature. Right, that should look really familiar after this week's assignment, right? Each one of these pages is 10 points, so total of 10 pages. Every page is worth the same amount. Electron configuration and counting protons, neutrons, and electrons. That's easy points, right? We all know how to count protons, neutrons, and electrons. And electron configuration is a little bit touchy, maybe, with some of the irregularity parts, but this is one that I really would love to give the entire class a 10 out of 10 on this section. Never been able to do that. I've gotten really close. I've had a couple of classes where somebody missed 1 point on electron configuration. So this is going to be the first class where I get to get 10 out of 10 for this page. There's easy points. Page of conversions. This is the one I was actually going to show you, though. I'm going to change this a little bit because we're not going to talk about polarity till after the midterm. I'm going to say, here's your compound. Give me the Lewis dot structure. I'm going to say, give me the electron geometry and give me the molecular geometry instead of this polarity section, because we're not talking about that yet. Right, so full credit for this is going to be do this step. Show me the Lewis dot structure. The electron geometry and molecular geometry, you can either memorize the names or know how to draw them properly and get the angles close-ish. I'm not going to get out a protractor, but I don't want you to draw these 90 degrees apart from each other if you're not going to give me the actual name. Asen? Yeah, so it's part on the slide decks that are on Canvas already, but then it's also in the text books that are back here. And if you Googled it, I'm sure that there's some good. There's lots of good figures. There's one that looks particularly good. I guarantee you in this book, there's a pretty good figure. Presumed also decent. Look at that. I opened up the molecular models right off the bat. So there's a whole section on it. If you want more details and more figures and things like that, you can borrow one of these. or if you Google it, make photocopies. Actually, if you're just interested in chemistry and you like seeing cool, there's a chemist in the UK that has an interest in graphic design who does these really cool infographics. Infographics aren't as cool as they used to be because there's a lot of garbage ones out there. But Compound Chem is the name of the website. This is another one, prints pretty well, especially if you have a color printer. It looks like, okay, well, here's your tetrahedral shape, and it shows it with a little bit more detail. Looks a little bit nicer than the way I can draw them by hand. But this is just a really interesting website in general for if you're into sciences. The history of carbon-14 and how radiocarbon dating works. Somebody asked a question about that the other day, right? It breaks it down for non-science majors so that you can actually, if you have a basic understanding of science, but you haven't actually studied any of this in depth, there's some cool stuff you can learn from it. Just a little plug because there's some really cool ones in there. You get, chemistry of perfumes, or chemistry of beer, chemistry of photosynthesis, where it makes some really cool looking graphics. All right. Is there anything else? All right, so, and there'll be 2 of those. Yeah. So we're not going to talk about that before the midterm. That when I teach this at the college, I do the order of the material a little bit different. We'll talk about that about midway through next term. So it won't be, it'll say Lewis dot structure, electron geometry, molecular geometry. Yeah. You can just say the names. If it's easier, it's either or. You can do both, but if you get one of them wrong, I have to take away some points. So pick one, pick which way works best for you. But if you're like, I think I messed up the name here, so I'm going to draw it too. That's a good way to hedge your bets. Harder to get perfect, but I can give more partial credit for that. Okay, so, but whatever works for you. If you're better at memorizing names and on that chart, go with that. If it makes more sense to think about it as 3D shapes, that's great too. Just know how to draw them. Yeah. Mm-hmm. I think it's usually a good idea. So carbon has more vacancies than most of our nonmetals, right? Because it's got 4 vacancies. So carbon, when you have a carbon's almost always going to go in the middle. Now, it also happens to be less electronegative than pretty much any of the nonmetals as well. So for both of our reasons, we usually put carbon in the middle. SO2, we did an example of the other day. So I'm going to go quickly through the Lewis dot structure. First version of the Lewis dot structure looked like this. That uses the right number of electrons. If you don't have this in your notes already, you can take my word for it. If you count up your electrons, it's the right number there. That fills all the valences. Does it fill all the valences? Not yet. But we ran out of electrons, so if we want to fill all the valences, we've got to make a double bond. So now we filled all the valences. Could we improve the formal charges? Yeah. Because the sulfur's got a +1 charge here. It owns 5 electrons and it's got 6 on the periodic table. This oxygen has 1 extra electron. It owns 7 and it's got 6 on the periodic table. So we can make an extra double bond Now both oxygens are 0, and so is the sulfur. Everything owns 6 electrons. And what is it about sulfur that lets us break the octet rule? It's in the third row. And what's unique about the third row? What do we get when we get to the third energy level? The d orbital. The d orbital makes everything more complicated, right? So the fact that sulfur is in the third row means we can go past 8 electrons. We need at least 8 electrons in the valence. But you can go up to 12. Can you go past 12? Not really. So now, right number of electrons, full valence, formal charge. What's our electron geometry? On the sulfur. How many things are taking up space around the sulfur? 3. These double bonds, they still count as being part of both valences, but they have to be in the same space. So it's kind of like, regardless of how many passengers a car has, a car takes up the same amount of space, right? So it doesn't matter that there's 4 electrons in this car. It takes up the same amount of space as this lone pair. Within reason. We want to extend that analogy a little bit longer. Lone pairs, because they're not stuck in between 2 atoms, they actually are a little bit bigger. So that's a little bit, maybe that's a lifted pickup in our car analogy. And this is a minivan. Can fit a lot of electrons in the minivan, but takes up a little bit less space than our lifted pickup truck does. But for all intents and purposes, a car is a car. They take up roughly the same amount of space. So, how many things do we have taking up space? 3, which means our electron geometry is trigonal planar. In our molecular geometry, then, there's roughly 120 degrees between each of these. So if we can't see that lone pair, we still have something that doesn't look linear. Right? So that's what we call bent. You'll notice bent actually shows up in 2 different places here, except that they do have different angles. The bent geometry, if it starts as trigonal planar, is going to be close to 120 degrees. Water is a good example of a molecule that's also bent. Except that this angle is more like 109 degrees, not 120. So, and we can actually measure these bond angles by basically we just get a crystal structure. We just get a water in its solid form, and we just bounce X-rays off of it. We shine X-rays through it, and most of the X-rays go right through it, but the X-rays that happen to hit a nucleus bounce off at a funny angle. If you measure what that angle is, you can figure out where that nucleus is that they bounced off. And then you can do some trigonometry and some geometry, and you can work backwards to figure out where everything is, where all the nuclei are. And so we can actually physically measure what this angle is. So we can tell the difference actually between a bent molecule that's tetrahedral and a bent molecule that's trigonal planar. But as far as the test goes, they're both just going to be bent. If you just wrote bent for each of them, that'd be fine. And really, remember how I was talking about how electron lone pairs take up a little bit more space, our lifted pickups? Really, this isn't actually quite 109 degrees because these lone pairs take up a little bit more space. They push the other bonds a little closer together. So it's really more like 105 degrees. And this is more like 118 degrees. But it's close enough that we can tell the difference and we don't bother splitting the hairs on that. If you just wrote 120, I wouldn't mark you down. But more accurately, it's a little under 120, the way that it says on the board there. Diego?
So for water, do we know that electron?
Well, partly because when we do the Lewis dot structure, we see that there's 2 lone pairs and 2 bonds. But that's also experimentally, you get water crystals, you get ice, and you bounce the electrons or the X-rays off of them. And actually, you can look at the X-ray crystallography. Is that what that process is called? And basically, I clicked the wrong button. Open image, new tab. There we go. So this is basically an overview of how X-ray crystallography works. But you wind up getting something where when you shine X-rays at a crystal structure, you get this sort of diffraction pattern. And from the angle of the different points in the diffraction pattern, you can work backwards to show where the different nuclei are. There's actually a really famous X-ray crystallograph of DNA. There's a higher resolution one. There we go. This is a really famous. That's really. This is DNA. Does anybody know who first figured out the structure of DNA? Ones that got credit for it are known as Watson and Crick.
She took this picture and then they took it from her and didn't tell her.
Kind of, yeah. They definitely didn't give her credit. Her name was Rosalind Franklin. Rosalind Franklin was the X-ray crystallographer whose research was actually focused in biochemistry, but not on DNA. And Watson and Crick had her research group take this picture, but then they totally misinterpreted it. They looked at it and they thought one thing, and then just like in passing in the hallway, they showed it to her, and she's like, "Oh, well, no, you've got it backwards. The bases go on the inside of the double helix, not on the outside of the double helix." And kept walking. And so they wrote it up, won Nobel Prizes for it, didn't give her credit until after she was dead. And they don't award Nobel Prizes posthumously. So she never did get any formal credit, but now it's pretty well known. I even have a sticker on my laptop that says Watson and Crick's big discovery was Rosalind Franklin's notes. Mm-hmm. And that's pretty much how it went. I think it was King's College at Oxford in the UK. It was apparently a very, very, very toxic place. To the point that she took a step down from being a full professor at one of the most prestigious biochemistry departments in the world to go do research on tobacco viruses in Virginia. And so she spent the rest of her career working on, I think it's called mosaic virus, if I'm remembering properly, that occurred in tobacco leaves in Virginia. It's a fascinating story. You wanted to read up on Rosalind Franklin, but that's the famous X-ray crystallograph that she took that she's best known for. All right. Last one here. Let's look at methanol. And there's a couple different ways we can write the formula for methanol. We can also write it as CH4O. We're trying to do the Lewis dot structure of this one. What is that going to look like? What's going to go in the middle? carbon, how many valence electrons do we have to work with? 4 from carbon, 4 from the hydrogens. That's 8 plus another 6 from the oxygen. So 14. So we're going to put carbon in the middle and then just arrange everything else around it. Is that going to work? Why not? Carbon's only in the second row, so it can only have 4 bonds. But we have 5 atoms. So we can't just do this, because if we just drew all the bonds, it has too many. That's a hard no. You cannot have a carbon with 5 bonds. But we have 5 atoms. How is that going to work, Maddie? Bond what to one of the hydrogens?
Oh, sorry.
We bond oxygen to one of the hydrogens. What if we did something like that? That looks a little bit more reasonable. How many electrons have we used now, though? We've used 10. 4 electrons left. Then we haven't used the right number of electrons. Where are we going to put them? Yeah, they can't go on the carbon for the same reason that we can't have 5 bonds in the carbon. We also can't give carbon any more electrons than it already has here. But the oxygen still has room for 4 more electrons. So that's why the conventional, what's called the condensed structural version of the formula, the condensed structural formula for methanol is not C4O, CH4O, it's CH3OH. Right, so that's the reason it's written that way. When you take OChem, everything when you talk to me, everything comes back. When you take OChem, you get more experience drawing this out and how this all works. But that's partly an attempt to convey, just in text, what this shape is, how things are connected. We can actually get more detailed if we had something like isopropyl alcohol. Looks like CH3, CHOH, CH3. We don't condense all that together to be C3H8O because we want to indicate where that OH is, what it's attached to. All right, so what's the molecular geometry going to look like here? We got to be specific, right? The carbon has 4 things taking up space around it, right? And we can see all of them. So the carbon we would just say is tetrahedral. And its electron geometry and its molecular geometry are both tetrahedral. The oxygen is going to have its own geometry, because the oxygen also has a bunch of stuff taking up space around it, right? 4 groups. So this is also a tetrahedral geometry, tetrahedral electron geometry, but the molecular geometry for the oxygen is bent. And when we put both of these together, we get an overall shape for the molecule. Right, and so if we were trying to draw this whole molecule in 3D, put the hydrogen there. Lone pair forward and a lone pair backward. So the oxygen is tetrahedral / bent. The carbon is tetrahedral as well. So basically, when they say molecular, the whole point of me doing this example like this is remind you that molecular geometry does not mean the entire molecule. If I don't make this really, really clear, some people would look at this and say, well, there's a total of 1, 2, 3, 4, 5 bonds and 2 lone pairs, there's 7 electron groups. Which is true, but not all around the same atom.
Oh, what makes it bend?
The fact that we can't actually see these, but when we measure this bond angle, it's about 109 degrees. So we can't see them because when we do that X-ray crystallography, there's no nuclei for the X-rays to bounce off of. So lone pairs don't show up directly when we're looking at these, measuring these geometries. But they show up because if they weren't there, then this would be linear. Right? If the electrons weren't taking up space, there'd be nothing to stop this hydrogen from being 180 degrees. Right? So we can tell by the angle of what is there that those lone pairs have to be there. Yeah, you can think of it like that. It's more like they're pushing the hydrogen away. Michaela? If I gave you something that's complicated, which I won't, I will try to give you things that only have one central atom on the test. Yeah, you can always either just draw this whole thing out, or you can just say, if we were to say we're asking about the oxygen, you could say, okay, you could say the electron geometry is tetrahedral and the molecular geometry is bent. You don't have to draw it, but if instead of memorizing all these names, if you find it easier to draw it, if your mind works better at visualizing things in 3D than memorizing names, that's totally acceptable too. You just have to get the bond angles approximately right.
Oh, on the midterm test, we have to write both the geometry, the electron geometry and the whatnot.
Correct.
But if it doesn't have any lone pairs, would we only just write the electron geometry?
So if it doesn't have any lone pairs, then the molecular geometry and the electron geometry are both the same. You just write the same word twice.
Okay.
So tetrahedral, tetrahedral. Yeah.
A lone pair, you keep on saying lone pair.
So lone pair are these electrons that are in the valence.
Okay.
These ones up here, they're taking up space and they're in the valence of this oxygen, but they're not part of a bond. The other term that gets used is non-bonding pair. It's a pair of electrons that's not part of a bond. Good question. Anybody else have questions about this? Yeah, Gloria? Not in this case because this carbon already has 8 electrons. If we did that, we just drew a carbon with 5 bonds, which we can't have. If this was a sulfur, then maybe if it got our formal charges closer to 0. Yeah.
So after the third row, how many can it have? It said you can have a max of 12 electrons.
Up to 12. We can do one that's kind of similar. It turns out that those noble gases, you actually can force those noble gases to form compounds if you have it with something that's electronegative enough. And they actually figured this out in a really funny way, interesting way. Interesting, at least, maybe not funny. There was a research group that the lead researcher studied fluorine gas a lot and properties of fluorine gas. And as a present, one of his graduate students made a glass bulb full of fluorine gas, but they didn't want it to be pure fluorine gas, and so they mixed it with a noble gas. I think it was xenon. They just filled it with xenon with a little bit of fluorine in it. And that little bit of fluorine, and you could actually see it because fluorine is kind of like a yellowish green gas. And they just made it as like a paperweight for him to put on his desk. And so he kept it on his desk, and eventually, after several years, he actually noticed some white solid forming on the inside of this glass bulb. But it's just fluorine in a noble gas. Noble gases don't react, so it should just all stay together. So he actually took it and they had to break it apart. And they tested that white solid, and they found out that it was actually a compound made up of xenon and fluorine. And they found out that it had the formula XeF4. What would the Lewis dot structure look like for that? Can we draw a Lewis dot structure that seems reasonable where everything has a formal charge of 0? Because that's really kind of our metric for is it going to be stable or not. Well, fluorines, we got 4 fluorines, they each bring 7 electrons, right? We've got a xenon that brings 8 electrons. So that gives a total of 36. So we can start by doing that. That just used up 8 electrons, right? Which takes us back to 28. How many electrons does each fluorine still need? Another 6 electrons, so 6 times 4. 24. So 4 electrons left. If we double bond, that's actually reusing some of the electrons we already have, right? And we can't just give the electrons to the fluorine because each fluorine already has a full valence and it's the second row of the periodic table. So fluorine's stuck where it is. We have 4 electrons left. We got to add them to the xenon. Xenon's the only thing we have that can break the octet rule up here, right? And now it starts looking a little bit crowded, but we used the right number of electrons. We filled all the valences. The fluorines all have a formal charge of 0. And how many electrons does that xenon have? 1, 2, 3, 4, plus another 4 that it owns outright. And it started with 8 as well, right? So everything has a formal charge of 0. Everything has a full valence. This is a stable compound. It's just a weird one. And it only works because fluorine is so reactive and electronegative, it can even force a noble gas to share electrons. And we know that this is the right shape for this because we had a solid crystal of this formed, right? So they did X-ray crystallography on it, and they found that it had a square planar geometry. In other words, the fluorines were all 90 degrees from each other. And it looked flat, but these other 2 lone pairs were sticking up and down. So the only reason that we discovered that, like I was there, was because the professor noticed that this, one-off gift from his student was breaking down in a way that it shouldn't be. Useful, right? Not really, but it's useful now that we know that it's there. Now that we know you can actually make compounds out of noble gases, we actually do use some of those noble gas compounds. Actually, maybe this one in lithium ion battery electrolytes. I believe that the fluid that they use in a lithium ion battery might be xenon fluoride based. Maybe no, it might be sulfur hexafluoride. Either way, there is some value to it, and because now that we know that these can exist, we can actually start testing them and figuring out their properties and things like that.
Can be used to help find and analyze trace metals that contaminate silicon rubbers.
There you go. Find and identify trace metals that can contaminate rubbers. How about that? And hey, the question that led us here in the first place was how high can the number of electrons go? This is about as big as it's going to get. You're not really going to see anything that goes past 6 electron domains. which for the most part means you're not going to see anything that goes past 12 valence electrons. In theory, they do exist, though. Jason?
How long can you like make a compound chain? So that you all around one.
There's actually not a practical limit. If we take that idea from of our methanol here, of instead of having one central atom and other things around it, if you have a bunch of central atoms, you can actually make the chain about as long as you want. In fact, most plastic materials, what are called polymers, where you take a bunch of small molecules and let them react together to make one big molecule. You wind up with one individual molecule that might actually be thousands or even millions of carbons long. But in biochemistry, we also see, who's heard of fatty acids? Fatty acid is a biochemical molecule that looks like this is what's called a carboxylic acid group. Carbon with 4 bonds, an OH, another oxygen there, and then get CH2, 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 so on until you get to about 20 carbons long. You just keep repeating that unit. And so a lot of times they'll actually shorthand that by saying something like that. CH2 18 times and then a CH3. And that's a really useful molecule biologically because basically every one of these carbon-carbon bonds that we formed here and all the carbon-hydrogen bonds we formed here have a lot of energy in them that your body can break down and turn into ATP. So this is the way that our body, that all multicellular organisms, I think, store excess energy. You eat excess energy, your body is designed to accommodate for long periods of starvation. So if you have extra energy around, it makes a whole bunch of these and stores them right here.
So if the middle atom was an element that's in the third row, that means it would have maximum 6 covalent bonds.
So the upper limit is more about space than anything else. In theory, you could go up to 9 covalent bonds, something that's on the third row and lower, because if you incorporated all of the d orbital, you could have a total of 18 valence electrons. But we don't really see anything just because there's not physical space around that central atom for 9 things. Even 7 central or atoms around a central atom is really, really rare. All right, how are we feeling about the geometry stuff? Yeah.
I just have a quick question.
Yeah.
So for like the linear with only 2 electron domains, between like 5 or 6 electron domains, if you did like the first whatever scan, like how would you differentiate that?
Those ones we would also have to do some other tests to get the empirical formula. So we knew that it was a 6-to-1 ratio, but it looks linear. Well, that even still wouldn't work. Basically, we have to look at the charges and the electrons. It has to have those extra electrons. This is one of the reasons why the Lewis dot structure is so useful, is because counting those electrons is part of figuring that out. We can confirm it experimentally, but experimentally, yeah, we can't really tell the difference between linear with 2 electron groups and linear with 5 electron groups. But we know how to count electrons. All right, let me. All right, let's talk about chemical reactions then. This is the last topic that's going to be, well, kind of the last topic. It's going to be on the midterm. Because if you look at the way the midterm's set up, so parts 1 through 6 are all things that we've already studied now that we've done these molecular geometries. 7, 8, and 9 are all going to be calculation questions, but they're all the same question presented a little bit differently. And if you look at them, they're all chemical reactions. And the question is always going to be, you have a certain amount of A and B. How much C can you make? Right, which we'll go through the process for figuring this out. But this is one of the biggest topics. If there is one concept that you take away from this class, if there's one concept you take away from this class, hopefully it's counting protons, neutrons, and electrons, I guess. But past that, is this idea that when a chemical reaction happens, we can calculate how much product we can make and how we can actually go through the math for that. Right, so it's going to show up 30% of your midterm is the same question asked in slightly different ways. And then the last one's always going to be a wild card. Basically, 90% of your points, you're going to know exactly what the problems are, just with different numbers or different chemicals. The 10th one is going to be a word problem, some sort of conversion word problem. Make you think you're on your feet a little bit. You don't have to get it perfect. It's basically just to separate A's on the test from B's on the test. You could get a pretty strong B and not even write a word on number 10. Is reasonable because you already know what parts 1 through 9 are, right? In theory, you could get an A on the test and not even touch this last one if you did everything else perfectly. But if you want that A, you're going to have to think on your feet a little bit, do a little bit of problem solving. It's not going to be anything as complicated as the black hole problem. It might get as complicated as, say, the aluminum foil question. What's the length of aluminum foil you can make from 1 kilogram of aluminum if you know the density? You remember that one? That one was doable, even if it was a little bit tricky at first. You'll get a fresh conversion sheet, fresh periodic table. And I think it should have everything you need. But like I've said before, I don't like memorizing for the sake of memorizing, especially in this era of everybody has a supercomputer in their pocket at all times. There's absolutely no need for you to memorize things beyond your polyatomic ions. Take the test? Yeah. So there will be a little bit of time pressure, but remember that most of these are actually going to be pretty quick questions to answer. 10, not so much. Like these ones, all you have to do is, okay, a square footage times another foot. Plug that into your calculator, round it properly, done. Right? Like this page will go really quickly. Counting your protons, neutrons, and electrons will go really quickly. Right? So there will be a little bit of time pressure, but I think there's not usually a huge when I'm grading them, at least nobody ever turns in completely blank pages. Everybody's at least has time to attempt each of the problems.
Regular class.
So it'll be an hour and a half.
So the key thing is to really study your practice midterm. If you guys study hard and you know how to do all the problems, then you should be able to run through the test really quickly. So what I see, if you don't know what you're doing going into the midterm, then yeah, time might be an issue. So make sure all the questions are basically not all but one are given to you. So study those so you know them in and out. You can do them. Basically, the numbers are just changed. So and some of the types of questions are slightly different. So if you know those really well, you should be fine.
So what I usually see with these tests, and I'm not going to hold everybody to the same standard because everybody takes tests differently, but the fastest students that are well prepared usually finish with an A. Right? The fastest A tests that get turned in are usually between 40 and 45 minutes. And granted, that's people that are really fast and also did the preparation. People that are really good students but didn't prepare, I guess people that know the material but didn't prepare by looking at the test, they'll still finish, but it'll be closer to that hour and a half mark. Right, so if you look at this, and I would also budget your time when you're practicing this. I can do this page in 5 minutes. You know where your limits are and set those times so you have an idea. If I'm spending more than 10 minutes on the nomenclature page, maybe I should have studied more. But at the very least, you can be like, okay, I'm going to cut my losses and I'm going to move on to the next problem. And if I have time, I'll come back to this one. Isabel? I don't know if it's published yet, but it will be. I guess I'd make it live at the beginning of next week. So you get a whole 2 weeks with it if you want to practice with it. All right. So all that to say, to give us a good background on these chemical reactions, because it's going to be 30% of the test. So some vocab, some defining some terms first. So we've talked about how chemical elements and atoms in general, part of that original definition of atomic theory was that atoms cannot be created or destroyed. They can just be rearranged. We now know that's not strictly true when we start getting into nuclear reactions, but we're not there yet. So for our purposes, for now, atoms cannot be created or destroyed. All that can happen is we can rearrange them. And when we rearrange chemical elements from different elements or compounds, we do so in a chemical reaction. Right? So that's sort of our definition of a chemical reaction, is that we took some starting material and we made new compounds or elements with it. Right, and the terms we use, whatever we make is called a product, which makes a lot of sense. You produced it. Product is what you make. The reaction arrow is basically there to separate the before from the after. So everything to the left of the reaction arrow is what you started with. Everything to the right of the reaction arrow is what you made. And the terms we use for what we started with, your starting material, your ingredients, are either reactants, or the older term that I still slip up and use from time to time is reagent. You see the word reagent literally means the exact same thing as reactant. Right, and so we're always going to have this before and after. The problem is, I guess it's not really a problem, it's just one more wrinkle we have to pay attention to, is that if we're taking these pieces and rearranging them, we might not be rearranging them into things that have the same ratios. In fact, we almost certainly are going to be putting them into different ratios. So how come we have 4 carbons on the left, but only 1 carbon on the right? It got split up. So if you're taking our C4H10, better known as butane, we're taking our butane and we're going to split up and we're going to make carbon dioxide with it. Well, how many carbon dioxides could we make? Got 4 carbons in our butane. So, and every CO2 only has 1 carbon. So in theory, we could make 4 CO2s out of that. We'll practice that in more detail here in a second after I define a couple more terms. But basically, we're parting out the butane. We're taking the butane, we're disassembling it, and we're doling it out to all the oxygen that's around. Because oxygen is really good at pulling electrons towards itself. And if we do that, I don't know, imagine some post-apocalyptic mountain town where people use car doors as sleds. You find a brand new car, it's got 4 doors on it. How many sleds can you make? 4, because you can part it out, right? That's basically all we're doing here is we're splitting stuff up and rearranging it. I don't know why car doors as a sled is what popped into my head. That's kind of weird, but we also you do a lot of food analogies when it comes to these, because this is kind of like a recipe. It looks a little bit weird in this case because we start with one big molecule and we make some smaller molecules. That's what parting it out came to mind. The other piece of information that's in this We also include the phase. Usually, if we're writing a complete chemical reaction, we include what phase of matter is each of these reactants in, because sometimes that actually matters. Some reactions only occur in the gas phase. So what else could we have? If I'm telling you that this is the physical phase, what does this mean? Gas. What else could we have? Liquid, solid. Any other phase you can think of? I don't mean the really weird ones. Aqueous. What does aqueous mean? It means you dissolved it in water. We actually have lots of chemical reactions that occur when you have different chemicals dissolved in water, and that technically is not a liquid. They're dissolved in a liquid. In fact, it could be argued that's all we are, is a bunch of aqueous reactions happening simultaneously. Jason?
Microsoft.
There are actually several other forms of matter. There's one that's actually named after Einstein because he theorized it would exist, called a Bose-Einstein condensate. But technically, things like superconductors are a different phase of solid. So even within solid, there's subdivisions, just like with diamond versus graphite. Diamond and graphite are both solid carbon. But we actually would want to be more specific, because if we took solid carbon and burned it in oxygen to make CO2, what phase is that carbon probably in? It's not just solid. We don't burn diamonds, right? Well, in theory, we could. They don't work it doesn't work very well, though. In theory, actually, a diamond has a little bit less energy. No, has a little bit more energy in it than graphite does, than coal does. But it just doesn't burn as well. And, you know, we tend to use diamonds for other things. But so we could actually even specify carbon as graphite. Occasionally we see phases that are actually a little bit more specific than this. These are the 4 basic ones. But there are other types as well. And a lot of organic chemical reactions happen in solution, but not in water. They happen in say you have benzene as your solvent, and we don't actually have a shorthand for solution dissolved in benzene. So in some cases, we just get more specific with our labels. But these are our 4 basic, most simple phases that we have to worry about for this class. All right, solid, liquid, gas, and aqueous. Again, if we talked about Earth chauvinism in this class, about how everything we do is designed around Earth as our environment. Like the periodic table is an example. All those molecular weights or atomic weights on the periodic table are specific to Earth. Different planets will have slightly different mixtures of isotopes, and so might have different atomic masses. This is another example. We are just big bags of aqueous reactions happening, and Earth in general has more liquid water than it has liquid of other solvents. So we care more about aqueous reactions. If we developed a periodic table on Titan that has liquid methane as the predominant liquid, we might have a shorthand for dissolved in methane instead of dissolved in water. But because we care more about water than we care about other solvents here on Earth, that's the one that gets its own special shout out. All right, so let's go back to the parting out the butane question. We'll talk about this concept, maybe do an example, and then we'll start with math in more detail next week. So if we take a butane molecule, we take it apart, we get 4 carbons. So that means for every 1 butane molecule, we can actually make 4 CO2s. But we can't just say, C4O2. because that's not carbon dioxide anymore, right? We can't just change the subscripts to make reaction balanced. Because if we change the subscripts, then it's not the same compounds anymore, and it's not the same reaction anymore. So if we're burning butane and oxygen to make CO2 and water, every one butane can make a total of 4 CO2s. Because we're taking all the carbon from the left-hand side and we're turning it into carbon dioxide. And carbon dioxide, by definition, only has 1 carbon atom for every 2 oxygens. So in order to balance things, we use what are called coefficients. And it's basically like we're taking that entire thing and multiplying it by that. We're making 4 separate CO2 molecules. So you can think of these coefficients that go in front of the chemicals, very similar to multiplying or distributing an integer in math. So we can make 4 CO2 molecules. How many waters can we make? 5, right? Because every water has 2 hydrogens, and we've got 10 hydrogens to work with. Cool. Now we balance our carbons and our hydrogens, which is what we want. In order for any of these to really work, we need to be ending with the same number of atoms we started with. Okay? Mm-hmm.
Where are you getting all the, since it's 4 times 2 oxygens?
I'm glad you brought that up because our carbons and our hydrogens are balanced, but our oxygens aren't. So we balanced these by putting coefficients in front of those compounds, right? So we could, in theory, do the same thing over here, right? How many O2 molecules do we need to make this work? We've got 8 oxygens there, plus another 5. So we need 13 oxygen atoms. Can we do that? Not with a whole number, right? We don't deal with partial molecules. So basically, because we need to get in, we have an odd number of oxygens on the right-hand side, and we can only add an even number of oxygens over here. So there's 2 ways in math that if you have an odd number and you want to make it even, there's 2 ways you can do it. What's the easiest way? What if we added some more to the carbon over here? If we times it by 2, we just did this. Now we've got an even number. Well, might be kind of hard to see, but if we do that, carry that idea forward, now it's not 4 CO2s we're making, it's how many? 8. We're just doubling everything we already had. So the 5 then becomes 10. Now how many oxygen atoms do we have? And now it's an even number, and we can put a coefficient over here. What's that coefficient going to be? We need 13 oxygen atom or molecules to get a total of 26 oxygen atoms. And now we should have the same number of every atom before and after. Michaela? It's not 10 anymore because we doubled the whole molecule. So yeah, exactly right. Right. So all this is a way of basically saying, if we're going to part out our butane, we've got to do it in a way that we can spread everything out the right way. And sometimes that means we have to double it in order to get everything to balance out. We don't want any leftovers.
So this is like an actual like
Mm-hmm.
it's like a radius if you do put this to 8. Well, 8 to
That's exactly right. That's exactly where we're going with this. For every 2 butane molecules that burn, we need 13 oxygen atoms or 13 oxygen molecules. But to do that, and when we do that, we'll get 8 CO2 molecules and 10 water molecules. Right, so this is just the same way as balancing the reactions a little bit like saying, okay, I have pizza dough and cheese and sauce, and I'm gonna make cheese pizzas. Balancing it is like saying, I need this many cups of pizza sauce for every pound of pizza dough and this much cheese to go on top. And then I can make this many pizzas. Right, so the balancing is just taking the qualitative idea of these are the compounds that are reacting and this is what I'm making, and putting numbers to it so we know what those ratios are. It's not just always, it's not always enough to just say, I know I have these ingredients, therefore I can make pizza. Sometimes you want to know how many pizzas you can make. And to know how many pizzas you can make, you need to know these ratios. All right, there will be a quiz this weekend. There'll be some practice with the molecular geometries and maybe one easy balancing reaction, but probably just the geometries and Lewis law structures. All right. All right, good job this week. See you on Monday.